Use case. First, let's understand the use case driving this project and its importance in daily life. The project is about predicting the mileage of a car model given the past data of various parameters that potentially influence the mileage. Let's imagine that we want to purchase a bike or a car. We know that there are dozens of models in the market that we can choose from. Each one comes with some or the other tall claims from the manufacturer. In case of bikes, some makers promise 100 km per hour pickup in 3 seconds. Some others claim 300-400cc engines, delivering heavy duty performance. Some others promise so much mileage. Now, mileage is a sensitive issue for everyone. Each one of us wants to know what mileage my favorite car or bike will actually give me. My friends who have used the model say, no matter whatever the claims, in reality, the petrol bill is cutting a big hole in their pocket. So is there a way by which I can predict, at least at a reasonable accuracy, how much mileage my favorite car or bike will actually give me? And this, given my style of driving, my route and traffic conditions. More importantly, can I know these details before making a purchase? Now the answer is yes. We are going to apply data science principles and machine learning techniques using Python to solve this problem. Regression analysis, single variable. Let us say we are trying to calculate how much distance a car will travel in so many hours. Assuming it's running at a constant speed s kilometers per hour. We know that the distance d in kilometers traveled by car in time t hours is given by speed s multiplied by time t hours. Given the constant speed of 40 km per hour, we can simplify this saying d is a function of t, or by an equation d equal to 40 into t. Graphically, this looks like what is shown in figure 1. In this graph, the distance traveled is plotted on the y-axis against the time taken t in hours to cover that distance on x-axis. A straight line given by y equal to 40x plus 25 exactly represents this relationship. Constant speed of 40 km per hour is the slope of the line. 25 km was the distance previously covered when the journey started. That becomes the y-intercept. This is an example of very simple regression equation with one dependent variable, the distance traveled, and two independent variables, speed and time. Out of the two independent variables, we held the speed at a constant value. Now coming to a real life scenario. Let's say we want to know the mileage of a car. Now there is no simple solution for mileage like the one above. Why? This is because the mileage of a car depends on many factors. Therefore, we cannot solve the problem by using simple algebra. This is where machine learning comes in. Such real-life problem can be solved using machine learning algorithms. Today we shall develop a project that uses linear regression. It is simple enough to understand, but very much useful to solve real-life problems in predictive analytics. Some common examples are forecasting future sales of a company, predicting the trend in stock market, anticipating next day's call volume in a call center, so on and so forth. Of course, we must keep in mind that there are many flavors of regression analysis besides linear regression, like non-linear regression, auto-regressive time series forecasting, seasonal ARIMA, triple exponential smoothing, and the recent neural networks with LSTM feature, etc. However, many real-life situations can very well be solved satisfactorily to the desired level of accuracy using vanilla linear regression. Now coming back to our today's topic, we are going to predict the mileage of a new car model that we are considering to purchase. Now linear regression multivariate. Let's see figure 2 to get an idea. In this graph, we see that mileage of various car models is plotted on y-axis against the respective weights in kgs on x-axis. What is the relation between mileage and weight? We can imagine that as the car becomes heavier, it burns more fuel. So obviously mileage goes down. But we also see that the points are scattered much more than the earlier example because of other factors besides weight that influence mileage. So obviously in this case, the solution cannot be just a simple straight line passing through all the points, like the one we saw above. We also realized that there are many other factors. So what next? How does machine learning using regression analysis helps us in solving this? Let's see. In general, linear regression, in linear regression, what happens is that the machine learning algorithms finds the best fitting straight line to model the relationship between input and output variable or variables. Remember that the algorithm in really understands only the numbers and is designed to find the best fit given any such vectors or arrays of numbers. Normally numbers denote points in space. Just to get an idea, in figure 2 we can see that one such base fitting line generated by Excel along with the regression equation y equal to 0.0077x plus 46.273. We should remember that this correlation is only between two variables, weight and mileage. However, we have seen mileage does not depend only on weight. In general, the input variables are called predictors or independent variables. Now let's look at figure 3. The vehicle weight, horsepower, displacement, year of manufacture, etc. are shown as the predictors. By the way, why year is a factor here? Because here the year for us represents the state of the technology. In other words, the models in earlier years were comparatively less fuel efficient. With every passing year, the designs became more and more advanced, and so the vehicles became more and more fuel efficient. Now it's somewhat simplistic to map advance in technology to year as a number, but in absence of better information, we are at least a step closer to reality. Continuing with the discussion, the variable we're going to predict is called the target variable or the dependent variable, which in our example is the mileage. For easy understanding, the charts are showing each pair of variables in a separate diagram. But in reality, they all act together. When there are three such variables, they can be represented along three dimensions. In that case, the regression line becomes a plane. For more than three dimensions, we have to imagine a hyperplane that human eye or mind cannot visualize. Essentially, what we do in machine learning is we try to minimize the error between the predicted and the actual value to fit the ideal equation y equal to a0 plus a1x1 plus a2x2 plus a3x3 plus anxn by trying out various combination of coefficients a0, a1, a2, etc. of variables or the factors or features as they are called in machine learning x1, x2, x3, etc. This is called optimization technique. So we are using one of the most commonly used optimization techniques, that is stochastic gradient descent optimizer, to predict our target variable, mileage of a car. In short, today we are going to solve a multivariate linear regression. That brings us to discussing our project. So problem statement. First comes the problem statement of the project. We define it as to predict the mileage of a car given the past data of various parameters that potentially could influence the mileage. Input data. Let's look at the input data. Figure 3, it has 394 rows and 9 columns. Each row represents an instance of a car model with its own feature value. Each column represents a particular feature, listing the individual values for the various car models like model name, the number of cylinders provided with the engine, then the displacement, namely the total volume of gas pumped into the chamber of combustion engine, the horsepower of the engine, the weight of the vehicle, the average acceleration the driver uses, the year of manufacture, and the country of manufacture. For example, if we look at one such model Toyota Corona, it has 4-cylinder engine, 113cc displacement, namely total volume displaced in 4 cylinders, 95 HP engine, 2228 kgs weight, 14 miles per hour acceleration, it gets on an average, manufactured in Japan and in year 1971. The introductory remarks given with the dataset tell us that it's an old data in the early 70s. During that decade, there was a big change in the car manufacturing industry in US. Technology changed from heavy and powerful 6 and 8 cylinder cars with poor mileage to lighter, less powerful 4-cylinder cars with higher fuel efficiency. The global automakers, mainly Americans, Europeans, and Japanese, all wanted to excel in fuel efficiency. Now, the solution: understanding the requirement, analysis of data, and design. It is important to remember that any data science project must be driven by a business requirement. The first thing we should do is understand what the customer wants. That is, to interpret the requirement from a user's perspective. At the same time, the scope of the work is limited by whatever data is available. Therefore, we work on the requirements side by side. We must also study the given data. We should not immediately jump to conclusion and somehow try to fit a machine learning model to get an output. Every data has a story to tell, and to establish that, a lot of preparatory work must go into the development. Studying the data is a lot of visualization and slicing and dicing of the data using various tools. We shall explore this practically when we execute the project. We see that MPG, miles per gallon, that is kilometers per hour in Indian context, is our target variable we want to predict. All the rest of the fields are the candidates for predictors. As part of our application design, we need to select relevant features by analyzing the behavior to decide if they impact the predictor or not. Many times, using intuition, we can drop some of the variables upfront that have no relevance to target variable. For example, some of the fields have identical or marginally varying values across the column. We can drop such variables outright. Some of the categorical variables like name, serial number, ID, etc. do not add value as a feature and can be considered for being dropped. In contrast, if the names occur in multiple rows and can be represented as a logical group, like we have US, Japan, etc. in our data, it can serve as a filter, say to form homogeneous group of items that belong to category. We find that technical definition of the term displacement of an engine tells us an important point. In the literature, the displacement is defined as the swept volume of all the pistons inside the cylinder of a reciprocating engine. Since displacement is the total value of gas pumped, it already includes the number of cylinders. So the column number of cylinders becomes redundant and need not be included in the input parameters. We'll see how we can make use of this information in our application design. The data contains a mix of US models, 8 6 cylinders, and higher horsepower, and higher displacement, and low mileage on one side, alongside newer trends of lightweight, 4-cylinder, lower cc, lower HP, higher mileage cars. We can segregate and process them separately, as we shall see. We shall also make use of the fact that in the chart years versus mileage shows in line with the above observation that mileage improved over the years. Summing up, we see that by using intuition and careful study, we can derive a lot of value from the data. Project details, part 2nd. That brings us to step-by-step execution of the project. At this point, I'm going to open my Jupyter Notes IDE and we shall execute various steps as shown in there.